In this mini lecture, we're going to be talking about linear regression. So recall that in bivariate statistics, there are two general methods that are used. One is correlation, where we're just interested in the association between two continuous variables, and the other one that we're going to be covering in this mini lecture is on regression. So where we're going to be making predictions about one variable as a function of the other by producing an equation for a straight line. So we're interested in a functional relationship and making predictions when we're interested in using a regression. So instead of just examining this association between the two variables, regression is used to produce the equation for a straight line, and then you can actually make predictions. So both of the variables for linear regression are continuous, but one variable is the independent variable and the other variable is a true dependent variable. And this is key when we're talking about linear regression. Just to recall from previous mini lectures on the Pearson correlation, there's no dependence of one variable on the other. So we have self-rated health and the number of physician visits. So recall with a Pearson correlation example, we have no dependence of one variable on the other. We don't know if individuals are going to the physician more because they have higher self-rated health, and so that means they're healthier, or not. There's no cause and effect here. It could go either way. When we do a linear regression, however, we're interested in the functional relationship because we may want to make predictions. So here are some data looking at age and systolic blood pressure among 33 adult women. So we have columns representing age, and then we have their systolic blood pressure, and we might want to predict, given a certain age, what might be the expected systolic blood pressure. We can plot this data and look at it. And here on the x-axis is age, and on the y-axis is our systolic blood pressure. Now when you think about this, it wouldn't make any sense to put systolic blood pressure as our independent variable and put it on the x-axis, right? Because we're not going to predict how old someone is based on their blood pressure. As a functional relationship, that wouldn't make any sense. So here we have age on our x-axis because it's our independent variable, and seeing how the systolic blood pressure would change as related to whatever the age is. I mentioned that in linear regression we're using the equation for a line. So we have y hat, which is our predicted value of y, is equal to a plus bx. You might also see y equals mx plus b. That's equivalently the exact same thing. When we look at this, we have y as our dependent variable, so it's the variable that we want to predict. X is our independent variable. B is the slope, so how many units you increase along the vertical axis for every unit increase along the horizontal axis. And A is the y-intercept, so it's the score on the vertical axis, or our y-axis, that the line will actually pass through. And for regression, what variable we're calling x and what variable we're calling y matters, because regressing y on x, so basically flipping the axes, is not the same as regressing x on y. Again, this is just the idea that we have a true dependent and independent variable that we're interested in looking at. So let's just look at this data again, where we have age and our systolic blood pressure. So we have a range of data points. And before we do the linear regression, imagine all of these data points without a line. So that's what you'd see, just the data points with no line. So how do we know where to put that line? What is that line of best fit? So you see that there's each of those data points that are there, they don't all fall on the line. There's some variation associated with them. And the idea with a linear regression, so I'll walk you through what this means. SS, of course, is representing the sum of squares across all of the data points. So here we have x on our x-axis and y on our y-axis. For all our values of y, we have some average value, so that's y bar. If we have a series of data points, here I'm just showing you one data point, which is yi. That's an individual actual data point that we have. And y hat is the estimated value of y. So that's always going to be falling on the regression line. If we want to know how far our actual data point is from a regression line, that's going to be associated with SSE, so that's the error. So how much our data point is different from the point on the regression line. If we summed up that across all of the data points, for example in the previous figure, that would give us our sum of squares error. The sum of squares regression is related to each of the points that fall on the line. So y hat, how much that differs from y bar. If we summed up across all of the points on the regression line, that would give us our sum of squares regression. And then our sum of squares total is going to be equal to those two things added together, the sum of squares error and the sum of squares regression. Same way as we've partitioned variation in previous modules. So sum of squares total is how much does each of the data points, or y sub I, differ from the overall mean. Part of that is due to the regression equation that gives you the line, and the rest is just due to error. So conceptually, we can think of the total amount of variation that each individual data point has from the overall mean of y as being comprised of two parts, or a total sum of squares is summed up across all individuals. So it's each data point minus y bar, square that, sum them up. So there's the sum of squares regression, and then the sum of squares error. And when we actually create a line, the line is based on what we're calling least square. So we want to minimize the error. We want those data points to not be really far away from the line. And you won't be asked to calculate the actual regression line. But you should know, because this is really important to know, is that when regression lines are made, is that they're minimizing the sum of squares deviations from the line. And here we have our regression equation. So our intercept, if we went all the way back to age of 0, would be at 81.54, and then the slope is 1.22 times the age. So with every 1 year increase in age, the systolic blood pressure could go up by a value of 1.22, because that's the slope. The coefficient of determination is R², and it is actually the square of the correlation coefficient. So the Pearson correlation coefficient is R. R² is the coefficient of determination. It ranges between 0 and 1. Remember, for a correlation coefficient, it can go from -1 to +1. So if you square that, it's only going to go between 0 and 1. And in correlation, R² is the proportion of shared variance between the two variables. And in regression, R² is the proportion of the variation in y that is explained by x. And often when you complete a linear regression, you'll want to know what that R² is, because it's how well does that line fit the data. And this coefficient of determination is the proportion of the total variation in the dependent variable, so y, that's explained by variation in our independent variable, which is x. And so this coefficient of determination is called R², and it's the sum of squares regression divided by the sum of squares total. So how much of the total variation is explained by that relationship between x and y. And of course, R² can go between 0 and 1. So when we look at this linear regression again, so I have the equation up in the left-hand corner, and then on the lower right side is our calculation for R². Again, you won't be asked to calculate this, but I took all that data from the table, calculated the sum of squares regression, divided by the sum of squares total, and we get a value of 0.515. So about 50% of the variation in y is explained by x. And if we wanted to know what the correlation coefficient is, we would just take the square root of this value, and it would give us a value of 0.718. So what can we do with a linear regression? Well, one of the things we can do is make predictions. So if we wanted to know what the expected systolic blood pressure would be of a 55-year-old, well, we can use the equation that we have. So this is our equation. We just plug in age, so that's 55, do our calculation, and we would expect that the systolic blood pressure would be 148.64. So we're just plugging in values. Now with linear regression, there are a number of assumptions. So the two variables have to be continuous, so interval or ratio scale. We assume that there's a linear relationship because we're doing linear regression and we're making a line. So if it's not linear, then doing a linear regression would not make any sense. We assume there's no strong outliers because outliers can have a strong effect on where the line falls. So if we have these outliers and we kept them in, they would really pull down or pull up the lines. So no strong outliers. We have an independence of observations. Our residuals are normally distributed. So again, the residuals are how far apart each of the individual data points are from the actual line that's there. Okay, so if you have very large residuals, they'll be really far from the line, but we expect that overall they're normally distributed. And our data are homoscedastic, so we have equal variance along the line of best fit. So in this plot, on the far right-hand side, we have homoscedasticity, so as we go across the x-axis, they're on either side of that line. It's an even spread. And on the center and the one on the left, that's called the heteroscedastic. So we have unequal variance. As you move along our values of x, the variance is unequal. So that violates the assumptions of regression, and you could do some transformation. Again, that just means, for instance, taking the log of the data, and that might be able to fix it. When we look at types of regression models, in the upper left we have a positive linear relationship. In the lower left we have a negative linear relationship. In the lower right we have no relationship, so as our value of x changes, our value of y does not change really at all is the trend. And then in the upper right we have some relationship that's not linear, so it would not make sense to put a straight line through that. A nonlinear regression is a more advanced technique. It can be done, but we're not going to cover it in this course. One thing that's really important to note when you're doing a linear regression and trying to make predictions is that you can't extrapolate outside of the range of the data collected. So this data here is ages of years for people on the x-axis, and then the length of their ear in millimeters. So all this data was collected from individuals that were 30-year-olds and older. So you can see the minimum age there is 30, and based on that data you can come up with this regression equation. The intercept is 55.9 millimeters or 5.59 centimeters, which would be really big on a baby. And so the thing to think about here is that this relationship between age and ear length is actually not linear from birth. And so if you're trying to use a linear relationship and extrapolate outside of the range that your data actually exists in, you might not be getting very good information at all because you need to know what that shape is. And one of the assumptions of linear regression is that there's a straight line equation, so you can only infer data within what you've collected because outside of that you don't actually know if it's linear or not anymore. So that's an important thing to note when you're doing a linear regression.